In this problem, we have a shunt-connected DC motor rather than a permanent magnet DC motor. This means that the magnetic field of the stator is generated by windings, or an electromagnet, rather than a permanent magnet. That electromagnet is going to burn up some power, and the problem tells us that it's connected in a shunt configuration, that is, in parallel with the source rather than in series with it. We're given quite a lot of information about the motor. We're told that the rotor resistance is 0.2 ohms, the speed is 1200 RPMs. We're given the current, and we're also told that the friction loss is 500 watts. Our goal is to find the load torque. We're not told anything about the stator in this problem, and it's not necessary in order to work it out. The first thing I'd like to do is apply the Kirchhoff voltage rule in order to find the back EMF. We can do this because we're told both the current through the rotor and the rotor resistance. This motor effectively has 190 volts across it. Since I know both the back EMF and the current, I can find the electrical power developed in this motor. 38 kilowatts shows up electrically right here, but that doesn't mean that 38 kilowatts makes it to the load. There's friction and mechanical losses inside the motor. Since the friction loss amounts to 500 watts, we know that 37.5 kilowatts is ultimately developed as mechanical power. We have all of the information now that we need in order to find the load torque. We were given the speed in RPM, and that's relatively easy to convert to radians per second. Now that everything's in SI units, I know that the torque is 298.4 Newton meters. In example 7, we looked at a shunt-connected motor. This means that the stator windings were in parallel with the supply voltage. In example 8 here, we're going to look at a series-connected motor. The stator winding is in series with the armature. We're given the stator resistance, the armature resistance, or the rotor resistance, the current, the speed, and the loss due to friction inside the motor. We need to find the output power and efficiency, and typically to do any calculations with power when you're looking at a motor, you have to find the back EMF. We can use the Kirchhoff voltage law to find the back EMF. We have a voltage drop across the stator given by the current times the stator resistance, and we have a voltage drop across the rotor given by the rotor resistance and the current. This works out to be 180 volts. The electrical power thus delivered to the motor itself is given by the back EMF multiplied by the current. 3.6 kilowatts is electrically delivered to the motor after accounting for resistive losses in the stator windings and armature windings. However, 3.6 kilowatts don't make it to the mechanical load. We know that there are 150 watts lost due to friction. After subtracting friction, we know that 3,450 watts are actually delivered mechanically. This is the output power. The efficiency is output power divided by input power. We have 3,450 watts mechanically delivered to a rotational load, and the input electrical power was 220 volts times 20 amperes. This motor is 78.4% efficient. In example 9, we're told that we have a separately excited DC motor. This means that the stator is not wired in series with the rotor, and it means it's not wired in shunt either. It means we have a separate power supply. This is advantageous because it allows us to adjust the back EMF constant. Since we're told here that we have a constant field current, we can basically treat this motor as a permanent magnet DC motor. We're given two situations in this problem. One, when the motor is operating at 1045 RPMs, and another when the speed is unknown. We need to find it. The armature resistance, or the rotor resistance, is a constant. It's the same in both of these situations. At 1045 RPMs, we're told that the motor draws 50 amperes. In the second situation, we're told that the motor draws 95 amperes. Let's find the back EMF in the first situation, using the Kirchhoff voltage law. We have all the information we need to find the back EMF in the second situation too. The only difference is the current drawn. The back EMF constant of the motor is the back EMF divided by the speed. Since it's a constant, we know that it's the same in both of these situations. At the first speed, we have 115 volts and 1045 RPMs. In the second situation, we have 110.5 volts and an unknown speed omega. These two quantities should be equal to one another. We've kept everything in RPM units this time. The speed is 1004.1 RPM. Notice that in the second situation, more current was drawn and more power supplied than in the first situation, yet the speed of the motor was reduced. That's because the motor is under greater strain. It's supplying more torque to a mechanical load in this situation. In the last example, we have a series-wound DC motor connected to a fan. Now, anytime you connect a motor to something, then it can change the relationship between torque and speed. In this example, we're given two different speeds. First, we're told that the motor draws 25 amperes when the fan is spinning at 300 RPMs. And then later, in part B, we're asked to determine the value of a resistor and the power supplied to a fan when it's only spinning at 200 RPMs. Let's start off with the equivalent circuit diagrams for both situations. Since this is a series wound motor, we have both a stator and a rotor. We're given both the stator resistance and the rotor resistance. We're told that it's a 220 volt motor and it draws 25 amperes of current at this particular operating point. In the second situation, we're told that there's an external resistor that's been placed in series with the motor. Let's call that resistance R. In the 200 RPM situation, the motor is definitely going to draw a different amount of current than 25 amperes. So let's label this current I sub 2 in order to distinguish it from the first situation, I sub 1, when the current drawn was 25 amperes. In each of these two situations, the back EMF will definitely be different. Let's label the back EMFs E sub 1 and E sub 2. For convenience, let's go ahead and convert the speeds into radians per second. 300 RPMs is 31.42 radians per second, and 200 RPMs is 20.94 radians per second. We can go ahead and write down equations for the back EMF using Ohm's law. We can apply Ohm's law to these two resistors in order to find the back EMF in our first situation. Since we know that the current drawn is 25 amperes, the back EMF is 195 volts. Let's go ahead and write down the equation for the back EMF in situation 2, but we're not going to have enough information to find it just yet. There are too many variables in situation number 2, so we're going to have to use some extra information from the problem in order to find the current and the resistance. We're told in the problem that the torque is proportional to the square of the speed. This means that the torque divided by the speed squared in situation number 1 equals the torque divided by the square of the speed in situation number 2. We have more information in situation number 1. Let's go ahead and find the torque. To do that, I can find the output power. I know that the output power of this motor is the back EMF times the current, and it's also the torque times the speed. We're not told any frictional mechanical losses for this particular motor, so we can assume that all of the torque ends up at the shaft of the motor. This equation is always correct, by the way. It's just a question of whether or not some of the torque winds up driving a frictional load versus a real mechanical load. We know the voltage, we know the current, and we know the mechanical speed, so we have enough information to find the torque. The torque here is 155.25 Newton meters. The output power is 4,875 watts. Since it's a 5.2 kilowatt motor, we can see that the motor is not 100% efficient. In this problem, the difference is due entirely to electrical resistance. Since we know the torque and we know the speed, we can now find the torque in our second situation. Our torque works out to be 69 Newton meters. I can now find my output power, since I know both the torque and the speed, 1,445 watts. The output power is also the back EMF times the current, so I have a new equation containing these variables. At this point, I have two equations, but I have three unknowns. I'm going to have to come up with another equation. This is the equation that I'm going to use. We know that the back EMF constant for a motor should be constant. My instinct is to write down the formula for the back EMF constant. That is, the back EMF divided by the speed. But in this particular example, this equation is wrong. The reason why this equation is wrong is because the magnetic field at the stator is not the same with these two situations. Although we have the same stator in both motors, we have a different current flowing through the stator. In a permanent magnet DC motor, the magnetic field wouldn't change. But in this particular series wound motor, the changing amount of current through the stator means that there's going to be a stronger magnetic field when the current is larger. It means that we have to use the back EMF constant that's per unit Weber in order to account for this situation. Phi sub 1 represents the magnetic flux through the stator when the speed is 300 RPMs. Phi sub 2 represents the flux through the motor when the speed is 200 RPMs. The magnetic flux is proportional to the current, so I'm going to write a new equation where flux is replaced by the current. It's important to keep in mind that this circled quantity is no longer the back EMF because flux is not equal to current. However, this equation is correct because flux is proportional to the current, and I'm comparing two different motor speeds. After plugging in known quantities, we're left with a third equation relating the back EMF to the current when the motor speed is 200 RPMs. We now have three equations and three unknowns. This allows us to find the back EMF, the current, and the resistance R. Part B asked us to determine the value of the resistor and the power supplied to the fan. We already determined that the power supplied to the fan was 1,445 watts, and we've just determined that the value of the external resistor was 7 ohms.